Hey guys, we're going to look over section 2.7. The first probably 8 slides will be a review, so I'm going to go through them pretty quickly, and then the last will be new material. Okay, so again, we remember we're looking at limits at infinity. And so now, instead of going to a value, we want to know what's happening, let's say this end behavior. So as my graph goes here, x goes to infinity, or in this direction. Okay. So we said that if it goes to a value L, okay, so as it gets to some number, then we can call that y equals L a horizontal asymptote. So looking at this example, as x gets closer to infinity here, we see it's getting closer to this line. So the limit as we go to infinity is equal to 7. Okay, and as x goes to negative infinity, that's in this direction, we see it's getting closer to 3. So we can say that y equals 3 and y equals 7, I said that backwards, are horizontal asymptotes. We mentioned that it won't always go to a value. It could also go to positive or negative infinity. For instance, this graph here, this graph, excuse that. So here, what do we notice here? In this graph of y is equal to e to x, as x goes to positive infinity, it goes to infinity. Okay, it gets larger and larger. And as I go closer to negative infinity, it gets closer to 0. Okay? We also have functions that we say oscillate. So we looked at the sine or the cosine function. They go back and forth. So as I get closer to infinity, I notice there is no single value, okay, that is going to it. It's not going to infinity or negative infinity. So we say that those limits do not exist. Now, some functions are easy to look at. So if we look at the power function as we go to infinity, all right, then we notice here, in this case, any power function here as I go to positive infinity, they're also going to infinity. Okay? If we look at this function, which is the limit as x approaches infinity, we can rewrite that as x over n. We see it gets closer to 0. So for instance, here gets closer to 0 in this direction and closer to 0 in this direction. Okay? When I talk about negative infinity, it does different things if I have an even or an odd power. So we notice as it goes to infinity, it goes to infinity, but as I go to negative infinity, it goes to negative infinity. That brings me to some rules, okay? So we want n greater than or equal to 0, Okay? As n is greater than or equal to 0, then as I approach infinity of a power function, it goes to infinity, whereas if it's x to the negative n, or rewritten as this form, it goes to 0. But if I'm going to negative infinity, I have to worry about if my function is even or odd. All right? But regardless of where it's going, if it is 1 over x to the n, it's still going to go to 0. Okay? We also mentioned that I can put constants in front of these values. Okay? If I put a constant in front of x to the n, it's still going to be infinity because a constant times infinity is still infinity. But here, it might change my value because based on the sign of my constant. We didn't visit this, but I want to bring this up. Okay? If I have a function where it's p over q, we're looking at p if p is even, okay, versus p being odd, it will tell us where my functions are going. Okay? But if q is even, then keep in mind x to the p over q is the same thing as the qth root of x to the p. Since it's the qth root, if it's odd, I can do it with any real numbers, but if it is even, it's not going to be defined unless this value is positive. So now, if I take a limit of a function that is the sum, I keep doing this, sorry. that is the sum or difference of values. Okay? I can use those limit laws. And the limit law says I can break them up into individual limits. Okay? The limit of a constant, of course, is that constant. Okay? We can bring out the constant for that is here. And this is the rule of x to the negative n of 1 over x to the n. So we know that goes to 0. Likewise, limit of x to the negative n goes to 0. So this goes to 3. So looking at this example here, this is similar to what I did in class, but remember I said I did it a little differently. If I were to do that similar thing, we saw that if it was a polynomial, it's just we could look at the leading coefficients. So we saw that this goes to infinity over infinity, which is an indeterminate form, so we got to do some kind of algebra. Okay, so if we divide out the highest term in our denominator, so if I take out an x to the 5th, because that's the highest term in my denominator, and then what do I have left? I have these terms here. Okay, these of course will cancel. So of course I now take the limit of this here. Taking this limit, we can do our limit laws and take the limit of the numerator and the denominator. And what do we notice? Anything raised to a negative power is going to go to 0. So that numerator is all zeros because we're adding zeros. But in the denominator, I have 3 plus 0 plus 0, which is 3. And so 0 divided by 3 is that 0. This is the case that we saw when n is less than m. That is always going to go to 0, so we know y equals 0 is a horizontal asymptote. I won't go through fully, but I'm going to tell you what's happening here. This is another way we did not do it in class, but if I take out that highest degree of the denominator, so that's that x to the n, if I factor that out from this original term, then it's going to cancel out of the numerator and the denominator, and I'm left with this numerator and denominator. Now remember, this is that x to the n minus m. If I take that term out, then I'm left with all of these terms here. Now keep in mind, if anything to a negative exponent is going to go to 0. So all these terms in between are going to go to 0. All these will go to 0. Okay? And I'm only left with, what are these? These are those leading coefficients. Remember the leading coefficients? As well as this x to the n minus m. And so if we go here and we're looking at the limit of a rational function as we go to plus or minus infinity, remember all these terms will end up going away to 0, and I am just left with these terms here. I can factor out my constants, a to the n over b to the m, and I'm left with the limit as x approaches plus or minus infinity of x to the n minus m. Now let's look at some scenarios. We looked at these scenarios. If they're equal, if we're only looking at those leading terms, the x to the fourths are going to go away. I can bring out that 3 over 7, which is x to the 0, and we just get that constant. Okay? If n is less than m, of course, when I take out that highest term, I'm going to be left with a negative constant. We know that goes to 0. 3 sevenths times 0 is going to go to 0. Okay? We didn't look at even or odd, and I'm not going to necessarily look at even or odd because it's also according to what's happening here. We're just going to remember to use our rule when n is greater than m. In both of these cases, we are left with 4, which should give me... So I noticed when looking at these that this is incorrect. So this n minus m being odd. Let's look at what I have written over here. Okay, so I take out my leading coefficients, my 3 sevenths from here. And then I do x to the 4 minus 8 minus 4, which is x to the 4th. So actually that is even. Okay, but we can just do negative infinity to the 4th power. It's going to give me a positive infinity, and a positive times this positive number here gives me positive infinity. Okay, if I'm looking at this one here, this should actually be odd because I take out my leading coefficients, 3 sevenths. X to the 7 minus 4 gives me x to the 3rd. So a negative infinity to the 3rd power is going to stay negative. And a negative here times a positive will give me negative infinity. Okay, so here this is to the new part. Okay, what do we notice here? These aren't polynomials. This is just a rational expression okay? That is not a polynomial. I'm still going to do the same thing we've done before. If we took out that highest degree in the denominator again, okay, which was x squared, because x squared is the highest in the denominator, they're going to cancel. And I'm left with this function here, okay? So if we notice, our n is greater than m, because 3/2 is greater than 2, so I know it's going to be plus or minus infinity. I just got to see where it's going to go, okay? Keep in mind, this is going to go to 0. Well, this is the simplified form, so let's get this one. This is going to go to 0. This is going to go to 0. This is going to go to 1, so it's going to be something divided by 1. But 3 times x to the 3/2, that's infinity to the, say, what is that? 1 and 1/2? Is that right? Yeah. Yes. So it's still a number greater. So infinity raised to a power that's higher than 1 is still going to be infinity. And so infinity divided by 1, of course, is infinity. And so this is just the special case of if it is not a polynomial. I'm still doing the same thing. I'm still going to factor out that factor. I'm still going to use my rules. And I just got to do some different math to make sure to see which is going to go to positive or negative infinity. This is also will help you, This section will help you to complete the rest of your homework, okay? We're going to look at this function here. It appears that if I take that square root of that denominator, it's going to be x. So it appears that n is equal to m, okay? It is, but not quite. We have to look at it. So I'm going to pull to the side and we're going to come back to this. Let's look at this example here, okay? So again, this is example we just saw, and it appeared that n was equal to m. But let's really consider that denominator. If I consider the denominator, let's rewrite it. We're going to take out that highest term, which was x squared. So we took out an x squared, and of course you agree that x squared times 1 plus x to the negative 2 will give me this here. Okay. And then using our laws for radicals, we can split this up because this is a product. So it's the square root of x squared times the square root of 1 minus x to the negative 2. Now, let's revisit this square root of x squared. We can't just say that that's x. Why can't we say that? Because we know that a negative number squared and a positive number squared will give me x squared. Okay? So I have to look at the absolute value of x, and it's according to what the function is. Let's recall what the absolute value is. So the absolute value is a negative x if x is less than 0, and it's a positive x if x is greater than 0. So for instance, if we say x is equal to negative 3, the absolute value of negative 3 is a negative, right here, of the x value, which is negative 3. And that's how we get the positive 3. Okay? And of course, if x is equal to a positive 3, the absolute value of 3 is just the x value, which is 3. So now let's consider the case. We have to look at cases because we don't know what this value is going to be, positive or negative. So if we're looking at x greater than 0, those are going to be the values as I'm approaching infinity because those are the values that are greater than 0. So this is our denominator. So if we want to find the limit and we have our numerator over, let's rewrite our denominator in this form. Of course, our x's will cancel, and I'm left with the limit as x approaches infinity of just 4 over the square root of 1 plus x to the negative 2. Now, I can use some limit laws and do the limit of the numerator and limit of the denominator, but what do I know is going to happen? This is going to go to 0, and then the square root of 1, so I'm just left with 4 over the square root of 1, which is just 4 over 1, and so this limit is 4. And so what can we say about y is equal to 4? It's a horizontal asymptote. Okay, now let's look at the case if x is less than 0. So this is going to be the values as we're approaching negative infinity. Now keep in mind, this is again, my denominator is going to be a negative this time because of what we saw earlier. Okay, and if we do this and we rewrite the expression, my x's are going to cancel. And I'm just going to be left with the limit as x approaches. And this time we have negative infinity of 4 over a negative square root of 1 plus x to the negative 2. Again, my limit laws. Okay, this will go to 0. Now I have 4 over the negative square root of 1. So I get negative 4. So I have y is equal to negative 4 is a horizontal asymptote. So we notice if I have a radical, okay, then I got to consider that this isn't quite n is equal to m. I can think of it as n is equal to m, and I can think of it as the leading coefficients of those leading terms, but I got to consider the positive half and the negative half. And so now I'm going to have 2 asymptotes. So here is the problem worked out again, okay? And what do we notice? If we look at the graph, it approaches positive 4 as x goes to infinity, and it approaches negative 4 as x approaches negative infinity. Okay. We have concluded this section. The first part is a review. Use these last couple of slides to now complete your homework.